All right, good morning, everyone. How are we all doing today? I'm doing good as well. Thanks for asking. So, did you guys get a chance to work on the example we were talking about last lecture? Yesterday morning, actually, yeah. The library example, I believe. Because we're gonna learn how to draw the schematic today, and we'll probably use that as an example, and a couple of other examples as well, but that will be the one that we'll be working from scratch. Since we already started with it, maybe it's gonna be a good example to work with. So yeah, did anyone get a chance to think about it? All right, that's not a problem. We were gonna discuss the whole thing today anyways, so not an issue. But other than that, any questions so far from yesterday about databases? All right, amazing. So for today, today's lecture is gonna be about, sorry about that, about relational databases and SQL. So we're gonna start off with relational databases. We're gonna see how it works. We're gonna see the theoretical part of it. Then we're gonna move on to looking into the schematic diagram, which is a very important part of planning out a database. And moving forward from that, we will be taking a look at some SQL queries, just the basic ones, because we won't really use it for our database per se. This is more like to give you an idea of how the database actually works in a very basic form, but likely we wouldn't be using these queries. This is just for basics so that you guys learn how to do it. I mean, if you guys want to practice on your own, definitely we will be showing you resources where you can practice, and that hopefully will be good enough if you want to carry forward with the relational database thingy. All right, so let's just wait for a couple more minutes and see if more people join, and then let's begin with our lecture. Okay, so let's begin. Yes, we do have class. I was just waiting for a few more people to join. All right, so let's slowly begin. Let me bring out the lecture. Interesting. Okay. All right. I believe you guys can see my screen. So as you can see, today's lecture is gonna be about SQL. Now, we've already seen about we've already seen in the last lecture what SQL is all about, right? Let me see in the chat. Uh, okay, I think someone has an urgent issue. Okay, so yeah, we have seen last lecture what SQL is all about. So let's talk about it a little before we begin. What do we know about SQL so far? It'd be great if you guys could answer. Like, what is SQL or why do we need SQL? What kind of benefit do we get from it? Any idea? Structured query language to query database. Okay. Organization. So yeah, SQL essentially, yes, retrieve data from the database. SQL itself doesn't really retrieve data directly like that. It kind of helps you rearrange the database. But yeah, it is pretty accurate, the answer. So SQL essentially is a query language that helps you work through the database without having to change everything. So it's essentially a language that helps you organize your database, you could say. So let's see what it is in a more bookish term. It is a programming language, but the jury's still out on that. Some people don't like it, some people like it. So it's a love and hate relationship with SQL. But yeah, it is definitely very useful when you're learning about databases because it holds the very basic knowledge of creating, organizing, and working with a database. So SQL kind of builds you up for future tools that you'll see. And having learned SQL or having learned how to organize or create databases using SQL will give you a better understanding of the databases itself. So yeah, like in front end, there's a way of thinking of organizing the code. In the back end also, there's a way of thinking on how you organize the code. So this will help you imagine better. When I say organizing the code, for example, when you're creating a website, designing a website, um, it's good to think of the website as a whole layout, to think of it as grids. Okay, so there are three grids over here, and each of these grids will hold this picture. So it helps you think of the website in a more structured way. SQL does the same by with its tables, relationships, and whatnot. Okay, let's move forward. So again, relational databases, we've seen what those are. Anyone with a short description, like a line or two, on what relational databases are? Very short, doesn't even have to be 2 lines. You could actually describe it with 1 line. Containing tables and relation among them. Exactly, you're correct. So relational databases are essentially a more structured approach that contains rows and columns inside tables. And we use SQL to kind of manipulate whatever's inside those databases. Moving forward, so the key features are over here are tables. Obviously, data is organized into tables, which are two-dimensional structures with rows and columns. Each table represents a specific entity. Example, customers, orders, products. So the thing about when you're creating tables, one thing that you really need to think about is the information that you're putting into the tables, are they relevant? That's something that's very important. By relevant, what I mean is now some things could be relevant, but then again, it's not required. Now, if I'm creating a table for customers, adding what do you call it? Uh, so say this is a system about a grocery store, okay? So I'm just looking for customer information. Now, having the price of random items in the customer table, that won't make sense, right? Because the customer table will only have customer information. Now, one thing you could argue is, okay, why shouldn't we have price of things on the customer table? We could have all the customers' orders there. But my point is, having that much information in one table, it's not very useful. We have a separate table for our orders. Now you may also ask, then why don't we connect the two? Like we could have a foreign key from the orders table in the customers. What do you guys think? Will that make sense, or having it the other way around, having the customer's ID in the order table makes more sense? Is my question clear enough, or should I repeat? Yeah, of course. So what I'm asking is, um, if I move to this, okay. So my question is, you see all these information in the tables, right? Now, ideally, when you're looking into customer information, you would want to see the customer's orders as well, right? When you search a customer's name. But now my question is, then why do we not have order ID as a foreign key in customer table? Instead, we have a customer ID as a foreign key in order table. Why is it happening like this and not the other way around? Anyone with the answer? Or should I repeat the question again? Okay, so someone says, distinguish them unique feature to achieving and manipulating with one of them we want to prevent repetitive tasks. Okay, then another says, because there will not be one data under that. It's not very useful. Then again, Esther says, because we need the information of the customer when the customer orders something. Okay, so um okay. So my point is, now we don't add order ID as a foreign key in customer table because we don't really have to navigate from customer table to somewhere else. The thing is, all these tables are accessible on their own. It's not really a connection where you're like in the customer table and you have to just move to another table or else you can just go there. You could also directly access the other tables too. So the thing is, we don't really have to make all these relationships that complicated. But having some relationships in these tables give it meaning. For example, having the customer ID in the order table makes sense because we would want to know who ordered that item. But having the order ID in the customer table is not very useful or is not as useful because we already have a whole table for all the orders. We don't have to repeat everything. We don't have to repeat information in random places of the database. Because if we do that, you'll see there's a lot of places where a lot of information could go. But then again, it's not wise to put the same information in different places again and again. So just having relevant information over there is good enough. It doesn't have to be the exact one. Exactly. Shorter tables and prevent repetitive tasks. So this also makes your um, database more organized. So if you're looking for something, you know where it is. You don't have to hover through different um, tables. So yeah, that's a very important thing to understand. Now back to this. Rows. Now, each row in a table represents a record or a specific instance of the entity being modeled. It contains data related to the particular instance. What does this mean? So, what it's saying is the rows will hold information for one specific entity. For example, if we are having, for example, order table, okay? So all the information over there, maybe price, then items, or even the customer ID and whatnot. All these will be represented by the order ID. So order ID in this case will be the instance, the specific instance based on which the entire row is gonna be modeled. Columns. Columns represent attributes or fields of the entity. Each column has a name and a data type defining the kind of data it can store. Okay, one thing you see over here, integer then varchar, varchar. So this is actually a way of describing strings in SQL. So varchar, it can essentially hold characters up to 255 characters. If you go more than that, it's not going to work. But I mean, for a database, usually 255 characters are good enough. You don't have to really go for anything more than that. But if you do have to go for something more than that, there are other variables for that. So primary key, we already know what that is, right? It's the unique key of the table. something unique to identify all the attributes or of a row, or in other words, all the data of a certain entity which is being recorded in a specific row. All right, then foreign key. Tables can be related to each other using foreign keys. So they just establish the relationship between two tables, making the kind of relation that helps us understand that this is connected to this. Do keep this in mind. The whole point of creating the relationship between the two is to make sense out of the information, not to navigate through it, if that makes sense. So the only possible reason that this might help you is when you're joining different datas together. For example, you're trying to display the customer information as well with your order information, then you just turn it into one big table. We'll see that shortly when we go into a demo. Okay, so that's that. Then we have normalization. So relational databases use normalization techniques to reduce redundancy and improve data integrity. Normalization involves breaking down large tables into smaller, related tables to eliminate data redundancy. So when designing a website, data redundancy is a very big issue because that takes up too much space, right? Remember I was telling you about the storage unit example. So if you just randomly throw stuff inside a storage unit, it's just going to take up too much space. But if you organize it and keep things where they belong or keep it in a neat and tidy way, you'll definitely be able to fit more things in the storage unit. The same idea over here. Um, less redundancies means more space for other information. Okay, so asset properties as well. Relational databases adhere to the asset. This one, it's very theoretical. This is good to know, but likely not as effective when you're not, I won't say not effective, but won't be something you'll have to worry about because when you're actually thinking of how to create the tables, this things come this thing comes pretty much on your own, but it's good to know what you need to do, which is essentially have atomicity, consistency, isolation, and durability. These properties are needed to ensure the transactional integrity. This means that the database transactions are reliable and data remains consistent even in the face of errors and system failures. So data needs to be consistent. You cannot have inconsistent data throughout your tables. Then they need to be isolated and atomic as well in a way that nothing is being repeated. Durability is something that also is very important, which shows that the data you are storing in your database is reliable. Moving forward, so primary key versus foreign key. Now, the definition of primary key is a primary key is a column or set of columns in a table that uniquely identifies each record in that table. It must have a unique value for each row and cannot contain null values, essentially IDs, right? The purpose it provides a way to uniquely identify each record in a table and ensures data integrity by preventing duplicate and null values in the primary key columns. Usage. Typically, it's used as a reference point in other tables through foreign keys and also automatically indexed for faster data retrieval. So in most cases, you'll see primary keys are IDs of different things. Names also work, but sometimes names become very similar, so it probably isn't a very good idea to have that as a primary key. Another thing that strikes me is probably email address. Email address could also be a primary key. Because if you think about it, email address are always unique. So that's something that could also be a primary key depending on what you need. So that could also be something to think about. So foreign keys. A foreign key is a column or a set of columns in a table that refers to a primary key to another table. It establishes a link between the data in two tables and represents a relationship between them. So purpose defines relationship between tables, as we've seen, linking data based on common values. Yeah, names can be unique, exactly. So names, it's a bad idea to have those as primary key, but emails, on the other hand, in most cases, I've never seen a email address match with two people. So I would say email addresses are usually very unique. And that's something, depending on your usage, you could have as a common name, as a primary key, sorry. But yeah, then for the purpose of foreign keys, we have enforces referential integrity and ensures the values in the primary key columns exist in the reference primary key column. Usage, it's used to create relationships between tables that we already know, helps maintain consistency and accuracy when dealing with related data. Okay, so all right, that's good. Any questions so far? All right. Okay, this example we've already seen. We already know how this goes. So I'll just roughly go through it. Over here we have this is just showing the idea of a primary key and a foreign key. So we have two tables. And over here for order table, we have a foreign key, which is customer ID, which refers back to the customer table that holds customer information. So if this is clear, we can move forward, right? Okay, I assume it's understandable. So schematics, the schema. Database schema is a logical arrangement or blueprint that defines the organization and structure of a database. It describes how data is stored, how relationships among data are handled, and how data integrity and consistency are maintained. A database schema includes various components such as tables, columns, data types, constraints, and relationships between tables. So, as it says, it's a blueprint that essentially defines the whole organization and structure of the database. So, it's very safe to say that it will definitely hold everything that is needed for the database itself. For example, the tables, the columns, the data types, the constraints, and all the relationships between the tables. So what does it look like? This is what a schema would likely look like. We have different tables over here, as you can see: orders, users, order items, products, countries. Okay, so hmm. So this example, it kind of just, as you can see, it's not as descriptive. This is just to give you an idea of what it looks like. But from here, you can see that the user ID over here is being used here as a foreign key. So you could say this ID over here is the primary key. The orders ID is the primary key for the orders table, and so on. Let's actually look at a better example and kind of make the connections ourselves. Okay, so let's kind of do this on our own. Let's annotate over here on the screen. All right. I don't think you guys can see it properly now. This should be good. All right, now help me out over here. So let's first identify the primary keys. Which ones do you think are the primary keys? Anyone? Customer ID. So I can just write down EK over here. All right. So yeah, now it says customer ID, product ID, order ID, employee ID. Correct. Okay, let's do it now. So I'm gonna write PK here as well. Here too. And here as well. Okay. So we have our primary keys set, right? Now let's talk about foreign keys. So for each table, which of the items or which of the attributes over here are our foreign key? There's a foreign key in the orders table, okay. Which ones are the foreign keys? Customer ID, employee ID, product ID as well, correct. So let's start drawing. Um, just gonna do this. Okay, so that's for customer ID. And let me get an arrow. Okay, so that's from there. Then we have product ID. Let me just get it from here. Okay, product ID. Right over here. And change my arrowhead. Goes from there to there. Okay, and finally we have our employee ID. So I take it from here and straight to there. And let me also write down that these over here are the foreign keys. FK, FK, again, and again, FK. All right, so is that good, or do we have any other foreign keys? So can we say this is a complete schematic diagram? What do you guys think? Yep, you are correct. So we do have all the necessary relationships stated. We have our tables ready, and we are ready and all set to create our database using this schematic diagram. Okay, so let me just take a screenshot of this real quick. All right. So, okay. This part's understood, everyone? Do we understand how we created the connections between the tables and everything? All right, amazing. Okay, so next we are gonna do our library example. But before we go to that, let's actually think about how these tables are structured and what kind of information are here. Yes, we did something like this at the very start of the program to just give you guys an idea of what's gonna be there for you in the backend part. This is a very basic concept and important as well. Yeah, so let's take a look into it. For customers, we have the customer ID, first name, last name, birth date, money spent, which makes sense. The total money spent should be there. Then anniversary, this probably isn't as important, but if you want, you could have it. This just shows, I believe, how long the customer has been with us. Then if you go to the products table, it's very neat. Nothing much. If you see, it's only the things about the product, nothing else. It's just the product ID, category, and price. We could have added how much of this have we sold, but that won't be as important over here because all that is gonna be inside our orders table. The entire point of SQL is so that we could just have these data in these tables and bring them out using our queries. That way, the tables are not filled with repetitive information. So, yeah, in this case, what do you guys think? Having the total number of units sold for this table, would that have been very useful? So, the question in chat, in order table foreign keys, in order I guess what you're saying is to have foreign keys, most likely we have to create a composite key, am I right? Yeah, it's composite keys are essentially the ones that already are there. It's something that we'll look into it later on, but for now, let's just talk about the very basics. For example, just primary key and foreign key in this case is good enough to just go on with our database. We'll talk about the composite key later. But like I was saying, what do you guys think? Having the total number of units sold in the products table, would that have been very useful? Okay, so Then my question for you guys is, do we or do we not have the products over here already in the order table? Okay, so if we wanted, could we bring out the information of how much of that product was sold from the orders table? Can we do that? Because remember, this is completely for us, this design. It's not for the users. They won't be seeing this. We actually can do that. So just like other languages, SQL also has conditionals. So if we just search up the product ID from the orders table, it will show us exactly how many times and how many people have actually bought this product throughout the course of our business. From that, if we want a total, we can set a query saying we want a total of all these for the whole column, you could say. Does that make sense? So yeah, some of the stuff is we have to bring it out from the databases ourselves. We can't really, there's no point in storing everything in different um, tables. It's always good to have them in related tables, but not repeating them over and over again. For example, in orders, the number of times this is sold is important, but also for products is important. But one thing is for sure that we need to have tables that only show the products itself. That way, the queries become much more easier. So Esther asks, why, yes, but why not adding the inventory in orders? Or how many orders have been ordered? Okay. And then Navita is asking, what are other info outside of the counting that we have access to that's built in? You can honestly do anything. It's the same as any other programming language. It's just you are manipulating whatever information is here. So for example, I will actually go one by one. So the first question was, why not adding inventory in orders, or how many orders have been ordered? So if you, like I said, over here you can see the product ID, and this means that this product has been definitely bought, right? So every time this product is being bought, it's gonna get recorded in the orders table. And from that, using our queries, we can find out how many times we have bought this order or this order has been sold. Sorry. Um, the query would essentially be something like show me product ID or show me, depends on what you're looking for. In this case, say we are looking for inventory, then we would just write a query that is showing us the product ID from tables, from the table orders. So that will show us every single time that product has been bought. Does that make sense? And that's good enough. I mean, for a database, and this is, keep in mind, this is only querying. So you're just bringing out information. You're not doing calculations in the database. Any sort of calculation that has to be done, you have to do it in your back end inside your code, where you're actually retrieving the data and showing it to the or displaying it to the front end. So those kind of calculations have to be done by you in a separate place, which is our backend file, not the database. Okay, but there's no field for the inventory to keep track of how many products have been ordered. So when we just ask for product information, we don't really exactly want to know how many items have or how many units of it has been sold. Now, depending on how you want to design it, but from the looks of it, from this schematic diagram, it doesn't seem very important because the programmer is actually bringing in all the information from the orders table and kept the products table only for viewing the information about the product. And the information about the product is only the product ID, the category, and price. This is strictly the information about the product. When you start talking about stock, the inventory of the product, it actually goes into a different kind of, I don't know what to call it, genre or a different kind of section, which essentially holds many other information, such as the total price of the number of units being sold or to which customers the units have been sold. That's why all that is inside the orders table and not the products table. Yeah, so if you see the order table is essentially working like the inventory table because it holds the inventory as well. This has not been designed to hold the inventory. Now, if you see that the inventory count is very important for you and you have to store the inventory count again and again for your system, then and then only having an inventory attribute in your order column or having a different table altogether is useful. But if you don't have to show the inventory count again and again, then, or not actually show, if you don't have to store the inventory count again and again, if it's not dynamically changing or it's not changing in mass numbers, then there's no point in having a separate entity for it. Hope that makes sense. If not, I can explain again. It all ends up with how you want to design your database or how you need your information. That's the whole point of having your own database or having this kind of flexibility where you can structure your database on your own terms, is so that you can structure it based on your needs. But you have to understand that what you need is actually what you want, or is it the other way around? What you want is what you need. Okay, so that is something to think about, that if you actually want this in your database, is this something you need in your database? Could this be done from your backend code? That's something to think about. Does that make sense? We're not really doing conditional queries every single time. Because think about it, when you are searching for information in a database, do you actually search it one by one, or do you just have three lines of code, which is essentially a loop that searches through every single block of the code when you're doing mock API? We just use the function dot map, right? It's a one-time code. So we just use dot map to check it once, and that's about it. It's the same thing for this. It seems like it's a lot of work, but if you think about it, codes kind of make it really automated. So you don't really have to query it again and again. Yeah, so it is similar. It is similar, but it's more structured. The query language is only if you're querying through the database. Now, one thing is taking information from the database and displaying it into your system or displaying onto the front end. But there's another thing about having databases is being able to browse through the database yourself. Say you're looking for someone's information, you just search up the person's name and you get everything under that person's name. Something like that. It this SQL part is completely strictly related to your database, nothing else. SQL doesn't help your front end. Does that make sense? SQL is only when you're going through the database itself. I think with the example, it is going to be clear. Yeah, we will definitely see examples, but again, this is something on a very basic level. You don't have to think too much about it because we won't be using SQL that um in a more deep way because it gets kind of complicated, and right now it's not very commonly used as well because as we've talked about, NoSQL, it's much more flexible and scalable for different kinds of projects. So that's being used more. All right, so let's move on to the next part of the code. All right, so let's try one ourselves, right? Let me create a new slide. Okay, so where is annotate? Let's go back to the library example. I hope we have time. Text. Okay. Yeah, you can definitely add more features later on when you need it. It's not a one-time thing. You can add as many tables as you want. You can add as many information as you want. It's all up to you. You can even change the information that you've already stored. You know how in mock API you used to use put or patch to change a specific thing from the API? So the query language also has something similar where if you want to change something directly from the database, you can do that as well. So you entered a name wrong or you spelled a name wrong, you could just change the name from the query. So that's something you could do. Okay, so right now we are talking about um, the library example. I understand yesterday I spelled library wrong, but I didn't correct it out. But okay, at least now it's correct. All right, so library example. Help me out with this now, guys. We probably know enough to be able to create a schematic of our own. So let's first think about the number of tables that we would need. So let's talk about that first. Could you just write it down in the chat what you think the tables should be and what their names are going to be? Anyone? So the thing is, for a small scale example of a library, yeah, three tables could just be good enough. So, so Veda, I assume borrowed books is essentially gonna hold all the information, such as what books were taken. Is it like a invoice kind of thingy that you're trying to say over here for table 3? Okay, all right. Yeah, that makes sense. Student books invoice. All right, so let's actually name them similar to what we have named yesterday and kind of talk through this in detail today. Um, all right, so I have 3, one there, and one over here. Um, okay, there's one, another line, and another. Okay. So let's call this one right here student. Let's call this one over here borrow info. And let's call this one over here straight up just books. Okay, so let's first think about the student table. Now, what's the first thing that we could write over here? The student ID, correct? Let's keep it small letter. Student ID, or just this. Okay. Student ID, and that will be the primary key. Amazing. Okay. Next, what can we have? First name. Okay. Now it actually gave a pretty detailed answer over here. Let's take a look at that. Library management system, username, password, user ID, name, account details, borrowed books, reserved book, returned books, lost books, fine amount, book title, author, publication. All right. Librarian. Yeah, this is actually a very comprehensive way of describing the whole database. Good work on that. But just for the simplicity of it, since it's one of our first examples, let's keep it as simple as possible. Let's not talk about librarians yet, not even fines. Let's just talk about the books itself and the students borrowing it. That's about it. So let's just keep it very, very simple. But the description that you have given in the chat for a broad scale library system, that would be a very good schematic. Okay, so over here we have student ID. Then I believe someone said first name. So if we're storing the name separately, I believe the next will be last name. What else? What else could we need? Email, right? Email, and then I guess phone number as well. All right. What's the last thing that we would probably need? Anyone? What's another thing that's very important for students' information in this case? Address, right? Because if they don't return our books, we'll know where to find them. Okay. Okay, so I think the student table looks good, right? What do you guys think? Or there should be more stuff or less stuff? Any comments? All right, amazing. So with that being said, let's go into the borrow info. So what's the first thing that we could probably put over here? Let's just call this invoice ID or borrow ID as well. Borrow ID. Okay, let's do it. Borrow ID. Next, student ID. But one thing, borrow ID over here, this is the primary key, correct? All right, then we have student ID. It has to be the same. Remember, the name has to be the same. Student ID, and this will be our foreign key. All right. Then we have the borrow date. All right. But since we are in the borrow date, we need a return date as well. And next, we are gonna have our book ID. Book ID. All right. So book ID over here will be a foreign key. You are correct, because this will be referring back to this over here. So I say for now, it's good enough. This much information. I mean, borrow info could definitely have a lot more, but I guess for now, this much information is good enough. So let's go for books now. As we said in that the other example, so we want students and books, these two tables to be very isolated or atomic in a way, so that they only carry their information only, nothing else, nothing related to transactions. They only carry their informations only. So in the case of books, we would ideally need a book ID. Let's keep it the same as the other one. Book ID. All right, and this will be primary key over here. Okay, then we have book name and author name. All right. Book name and author name. Okay, so I think this right here is good enough for the books. All right, so what do you guys think? Is this okay as far attributes go? Right, status could actually be a good one as well. But then again, like we said, we can actually no, status works. We should have the status over here. Doesn't really get rid of the, okay, status. Maybe add borrow ID. That's fine to see book availability. Okay, so this is where I was explaining the same thing as the previous example. So we can actually figure out so the availability, it's gonna be there. We're gonna hard code it from our code, from the backend part of our code, into updating the books as it gets returned from the system. Let me see with the chat, because status should be on borrow info. Okay, so one thing, borrow info, we already have the borrow date and return date. We don't really, we do need it actually. We actually do need it, but they're not the same though. Like, um, wait, let me just write it down over here in this way. Status. Okay. Okay, so we do have a status here and in the books as well, but see this, these two, this status and this status, they will be showing the same result, but they're not really connected to the database itself. Okay, we're not really getting this information from here. This information, the status, we would likely be updating from our system itself, because once the user returns it, we calculate it from our code and then we update it to the database anyway, right? Exactly. So we can calculate it using the borrow date and return date. We don't really need to do any calculation on spot using the query language in the database. We will be doing that through our system. Because when the user returns something, we would put it to the website. We won't be putting it through the database itself, right? So that's why all that calculation and the conditionals are being sent from the code itself into the databases. Now, we want to keep our databases as neat as possible. I would say this is pretty neat. It shows the information that we want to see for each of the different tables, but we are not oversharing, if that makes sense. So I have a question over here. Why adding status in book table to if we can take it from borrow info? So the reason behind having status in books table is so that when we go to the books table, we can just see on the side if it's available or not, just a glimpse, if that makes sense. No, these statuses are not foreign keys. So let me just rename these into, these are not duplicates as well. These are just information that both of the tables should have, but likely they don't really need to intertwine. It's not really duplicating the variables itself. So we can add borrow ID as foreign key to get the status. We can, but the reason I am not doing that is because if we do it, it's gonna look something like, something like this. And actually creating a code for this becomes very difficult from our end. So that's why having a relationship like this, where both these tables are referring to each other, this is definitely possible, but having that kind of code, it kind of gets complicated at one point. So it's better not to have that kind of relationships unless it's absolutely necessary. In this case, it is not necessary to have that, so we won't do it. Status over here. Does someone have a question? Someone's mic is on.
Nothing else, by the time you leave my class, you will be in better shape.
I am not sure whose mic is on. Okay. Chaman, you have a question? Okay, I guess not. Let's get back to the example. Okay, yes, like I was saying, you guys can hear me, right? All right, perfect. So yeah, like I was saying, this is not really a duplicate. We can have same information in different tables, even though they are not connected. Now, one thing is arguable whether if having the status over here is important or not. This is actually something that I'm thinking as well. Um, you know what? This already has the borrow date and return date. This doesn't really need a status. The whole point of having a database as descriptive as possible is so that we can figure it out just by looking at the database without making calculations. Now, if we have the borrow date and return date, we won't really need the status over here. So actually, we can get rid of this. And I think I will. Okay. So in the chat, I see you want to avoid extra work to access only the book table. I'm not sure I understand that question. If you could elaborate. It's how the books is going to calculate the status of a book if there is no borrow info in the table. Okay, so understand this, okay? I think I need to draw something over here again. This is mock API. Did we do any calculations on mock API, or did we actually do calculations over here in our code and send the information to mock API. So we used to retrieve information, do calculations, and send it, right? In our code. So exactly, it's the same thing for us over here. Now, SQL won't really do the calculation for you to find the difference between the borrow date and the return date. You will have to do that from your code. And once you do that, you push it into the database. Does that make sense? So this is entirely just for searching through our database. You'll see when we get to our example soon. Okay, so let's get rid of these two. But okay, so we will have access for the other tables info. Yeah, I mean, you can have access for any table. You have to just declare it. You have to just, you know how you get information from mock API. It's very similar to this, but it's going to be a little different for SQL. But you still can get information from the database and post information into the database. It's the same concept. But luckily, you wouldn't have to think of anything this complicated because we wouldn't be going much deeper into this. Oh, no, 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 no. Don't think of it as like blocks. The whole structure is different. Every table is accessible separately. You don't have to go through blocks. Yeah, yeah, it's not like that. It's not like you need to have a foreign key to access the other table. You can access all the tables separately. That is not an issue. All right, so okay, so we can say that this is good enough for attributes. So now let's try to create our connections. So we have our foreign key, primary key for student over here and foreign key over here for borrow. So we can say that this is actually referring to, or this can be added to this. Student information can be added to borrow info. Also, book information can be borrowed to borrow info. Does that make sense? It's very simple. It's just so that you have an idea of what a schematic diagram looks like. And that's basically it. It's just figuring out the attributes, the tables, and creating the necessary connections. But this is essentially all it is. Take a screenshot of this. Samina, you have a question?
Yeah, I just wanted a clarification for the status. So you had status in both borrow info and borrow, so in books. So what made you change it to books and remove it from borrow info?
Okay, so the reason why at first I put it in both because I thought, okay, having the status won't be a bad idea. But then I realized that in the borrow info table, we already have the borrow date and return date.
That's right. Yeah.
So likely if the person didn't return it, the date would be pushed or some other thing would take place. This is a very simple example. We're not talking about fines as of yet. But likely there would be other things happening if the person didn't return. For now, let's just think everything is going according to plan and the person returns on date. So we already have the borrow date and the return date. So we can already figure out what's the status, if the book is available or not, or the books that the students took is sent back to our system or not. But the books, on the other hand, it requires a status because when you search up the books, you get the book name, the author name, the book ID, and all that. But on the side, when you see the status as well, whether it's available or not, then it gives you an idea. Okay, so I have this book in stock. So say if someone comes to you and asks, oh, do you guys have this book with you? You can just go into the books table and just look it up. You can just see the books table and it's good. You can see the status. Okay, it's available. And if it's not, you say it's not there. But if I had the status in the borrow info, then I would have to go through all the transactions for no reason, right? But the customer only, or the student only wants to know if that particular book is available or not. So that's the whole reason behind having the status over there. You just have to kind of think about the use cases for those on what kind of situations might arise. Because all the tables, they're accessible from your code, but how you design your database is gonna definitely help you on finding information faster from the database directly. There could be a book lost as well. Yeah, could be. So, but we haven't really dealt with that over here as well. If you want a book lost situation over here, you would have to have a book count as well. But we're not really going there yet. That, like, from what I've seen so far, adding one small information will actually create another small information, leading to us creating multiple tables here and there and making it more confusing. So, but the schematic diagrams, usually you should take some time, think about it while making it. It's not really something you rush into. This could go into status. Definitely book lost could go into status. How I would do it, I would have a book count over here. And if one got lost, I would just deduct that one from there. That's about it. Because I'm pretty sure, I don't know. Actually, do libraries have multiple books of the same kind? I don't think so, right?
Yeah, they have. They
Okay,
have.
so then I mean, instead of having a book lost um
I think
attribute,
we
we
can
could
actually keep it in the status, and if you want to see any books lost, then we can just say, status, which has the status of lost. How many are there? So we will know.
exactly. Exactly. We would ideally have like a book count, right? Where we would see the number of books over there. If one's lost, then it's gone from the count forever. But if it's not lost, it gets added back when we get it from the student. So yeah, that's something. Because I mean, for a library system, there's a lot you have to think about. There's also the fact that some books might never come back from the students. So that's something to take into account as well. But those are like for broad scale situations. Right now, this should be good enough as an example. All right, so, okay, this one's done. Let's do one thing. Let me see how much work I actually have left over here. Okay, so not a lot. Let's do one thing. Let's go on a 10-minute break and let's come back and we will take a look into our SQL queries, all right? Okay, so I'll stop sharing here and I will see you guys in 10 minutes. All right, we are back. Let me share my screen again. Oh, there it is. Okay. All right, I believe you guys can see the screen with SQL on it. Amazing. Okay. All right, can you guys hear me? Perfect. So we know already what SQL is. It's a structured query language. It is a programming language specifically designed for managing and manipulating relational databases. SQL provides a standardized way to interact with relational database management systems, allowing users to perform various operations such as querying, updating, inserting, and deleting data in a database. It's the very definition of it. Key features include data query language, data definition language, data manipulation language, data control language, transaction control language. So all these are different, what do you call it, queries. So the first we have is select. It's for querying and retrieving data. Then we have create, alter, drop for defining, deleting, and whatnot. Then we have insert and update to include and get rid of using delete. So the difference between drop and delete is drop, we use it usually to drop the whole database, the whole table, you could say. And delete, we use it to maybe delete a single row or something. Yeah, and I mean, these are probably the more important ones that you'll see. This is essentially what a SQL table looks like. So how about instead of this, I show you guys how the actual thing works. Let me just open up SQL. Okay. Alrighty. You can see my screen, right? Okay. So I am using this online SQL compiler. Definitely using MySQL, the software is much, much better, but since we won't be going into too deep for that, this is good enough. So yeah, I will be at least using this online SQL compiler over here. As you can see, we already have a couple of tables given. This books I added earlier, which I will now delete using drop table and books. So let's see if this works. Okay, so as you can see, the books table is gone, and we will be creating the whole thing from the start. Okay, I wonder. Um, okay, I thought my screenshots are saved over here, but I guess not. Oh, interesting. Okay, I'll figure that out later, but that's for later. I guess we remember what the tables look like, right? So, okay. Let's create a table with primary key now. What was the first table? Students, right? Okay. Um, right. Okay. So let me just write down the query over here. So in order to create a table, we start off with the query that says create table. And let's call this students. I will open it up. Keep an eye on the syntax on how I'm doing it. And the first would be student ID. And I will write down INT primary key. So this right here is being declared as a primary key. Wonder if there's a better way to declare the primary keys. Okay. Interesting. Actually, we could also write it down like this at the end. But let's first list all our information. So we had student ID, then we had first name. I will call it first name, and this will be varchar 255. So this can hold max 55 characters. Then I will write down last name, and this is going to be the same variable type, 255 characters. What else do we have? We had email, and I will use the same. Unfortunately, this does not give you predefined options, so you kind of have to code it yourself. Why do we call the student ID? Yes, these are attributes or properties. So you remember how we structured the table under students? Every single attribute will be looking like this on the table itself. On the schematic diagram, we write it one by one, but over here, we will be declaring it like this. These are going to be all the attributes over here.
Oh, I was just wondering, is like the name, like just curious, like the naming, like do we call those attributes or properties?
Oh, these are attributes.
Okay.
I think properties also work, but I always call them attributes, the columns at least. And the rows, I call them tuples. Okay, so moving on, we had email, and lastly we had phone. So for phone, I'm gonna call this a character as well, because I don't really need to do a lot of mathematic operations with that. Okay, so that being said, I will write down the primary key now. So primary key is gonna be, Okay, I think I need some space. Looks better. Think you should write primary key and null at the same line of the variable or field definition. We can do that. There are multiple ways you can do it, but doing this, I'm doing this so that later on when we have the primary key and foreign key, you'll understand how we're doing it separately, just to keep it more detailed. So primary key, I'm gonna call this student. Honestly, this, I'm just trying it out. I've always declared it in one line, but I think this will go better with, okay. All right, that's good. I will close this off. Now let's try to run this. Syntax error. Interesting. So because
Maybe
of
start
this.
put a, yeah, semicolon.
Yeah, because of that. Okay, so I should have it over here. Students. It's been a long time since SQL. Okay, so we have it over here. Let's get rid of this then. The table is created. Yeah, SQL, it's been a while. Okay, so one of the tables is created. Let's create another one, which was borrow info, if I'm not wrong, right? Borrow info. Let's call it this. So inside borrow info, we had, what did we have? Okay, we definitely had the borrow ID. Where does the table appear? Well, it's right over here at the bottom, as you can, if you can see. So all the tables are on the side. Oh, wow, no. No, God, this went away. Yeah, that's the problem with these online thingies. I guess we're doing it again. All right, so let's just do it again. In SQL software, the interface is different. We really haven't gone to that because then there's a whole installation process for that. So, but the interface is a little different, but it's not that difficult to be honest. It's very self-explanatory. So I'm gonna
Can you,
create.
Christine, can you write this in a notepad and then copy it over there? So it would.
Good idea. Let's- All right. So let me write it down over here. Great. Now, actually, let's write it down over here. I'll just copy it over there because this kind of works with the syntax. The notepad won't have the syntax for me. Create table, and then I'm gonna call it students again. Let's go do this faster this time. Student ID. This is gonna be int. And we had first name. First name. Varchar. And it's 255. Nancy. So it's gonna be last name. last name, and I believe this was email and phone number, right? Phone number. Perfect. Okay, so let's actually finish. Oh no, primary key. Forgot. Primary key. Simona, your question?
Yeah, any reason why you wrote student ID in small case and student and ID you put an underscore, in the rest you're putting a space?
Oh no, I'm just used to doing it like that.
Okay.
It's no, there's no specific reason because you can write it the same way if you want, but
I thought it was an integer, perhaps that's why it has a different handling. Okay.
no, it's just I'm used to doing it like that. Okay, so primary key is gonna be student ID. And close, run SQL, it works. Copy this, Command C, Command V, amazing. Ah, interesting, okay. So it's not actually taking the space, that's my fault. Mhm. Okay, so this is okay. Just copy this. X, drop table, students, and run SQL. Okay, paste this, run it again. There you go. Okay, now it's better. So it doesn't actually take the space in the name. All right, so this is good. We have one table. Let's change it to the second one, which is borrow info, student ID, and okay. And over here we have borrow ID. It's gonna be int as well. Let's change these to book ID. Book ID. Oh, all right. Okay. There's one thing that I have to do first. I have to create the book table first. That's because this one is gonna have a foreign key from the book table, and if I don't have a reference, I won't be able to do that. So that is going to be an issue. Okay. Um, 1 second.
Can't we update it later on with the foreign key?
We can actually. That
Because
is
because every table will have some foreign key or the other, right? And
true. Um, yeah, I think we can. Let me just check real quick. Because I've always like created the foreign keys at the very beginning, but I'm pretty sure inserting is possible. Insert foreign key. Huh, interesting. I'm just checking something real quick. Okay. I think we can, but I think it takes a lot more work over here. let's just do all of it in one go. I think that's gonna be easier for us. Okay, so let's do the book one first. Let's get rid of this. Book ID then should be here. This is gonna be book. And this is gonna be book name, author name. Cut this off. Over here, I will put in book. Yeah, because then you need separate queries and the tables need to be joined, I think. I have to look into that. But okay, let's do this. I think everything should be fine. Book ID, everything is good. Run SQL. We have a book table here as well. Perfect. Okay, so now I will make sure I have more stuff here. Interesting.
Can we write multiple create tables and run SQL at this in a batch?
Ideally no, because then I think this is gonna keep on creating more and more tables. I haven't tried over here because this is a relatively new website that I'm using. But I think if the whole prompt reads the entire code and it will keep on creating more and more tables. I mean, we can try it out definitely, but let's just finish up with the work in hand first because we don't have a lot of time. Borrow info. I'm gonna have a borrow ID. INT. Perfect. Forgot what did we have next? Okay, book ID as well, right? Was it small? Yes. Book ID, INT as well. Then I had borrow date. Borrow date. Let's keep it varchar over here. Then return date. These are unnecessary. I think that's good enough. So that's the primary key. I'll do a comma, and I need to do a foreign key over here. So it's gonna be
That will be the foreign key. Student ID will be foreign key and borrow ID will be the primary key.
right. If we have to change this, this is the borrow ID. Borrow ID, foreign key should be, actually we have two foreign keys. Foreign key is gonna be student ID. Student ID. Okay, the dash in between, and then references. For every foreign key, we have to add references as well. And it is gonna be, in this case, students. Did I have a S in the name? I did. So students, and inside this, I'm gonna write student ID. Okay, so this seems fair. Next line, same thing. Let me copy this. I'm just gonna change this to book. I'm gonna change this to books. And this one to book as well. Okay, that seems fair. This one doesn't have a S. Let's try it out. Okay. This is also created. Now let's add some queries. Preferences. Are you talking about the references over here? Or references, we're essentially just referring which table we are connecting it to, or which table this belongs to. In this case, the student ID belongs to the students table. Does that make sense? All right, amazing. The foreign key is the primary key of which table? Exactly, that's what's happening here. Okay, so let's get rid of this, and I'm just gonna write down insert. Okay. All right. So I will write insert into. What's the first table I want to insert? So let's try out students. Nor borrow. Let's try students. Okay. So insert into students. It's not working. It is now. Insert into students. And inside this, I will name all the attributes over here. In this case, my attributes are student ID. Okay, there's an I missing. Student ID, then first name, comma, last name, and email and phone. Email and phone. Perfect. Okay, that works. And then I am gonna write down the values. It's very much similar to human language, to be honest. It's not enough. So Esra asks, do you have to write the specific references table info? Or is it not enough to just write the table name? No, you have to write down the primary key as well. So you have to write down which table you're referring to and which key it is. So inside values, let's write down, okay, let's first write 1, comma, let's call this John, comma, Doe, comma, okay, this should be, just write gmail.com. Johnny at gmail.com. All right, and lastly, I should have the phone, which is, let's say, random numbers. Okay, this should be good enough. Let me run SQL. Let's see if this works. Yes, it is recorded over here. As you can see inside the students, it's done. We can add more. We just have to change the numbers and John Smith. Just call him. Okay, that's done too. Dave. Okay, keeps on piling up. We have 2, that's good enough. Let's add a few books now. Insert into book. And can I just copy these? Is that possible? Okay, much easier. All right, so inside this, let's put in book ID 1. I'm gonna write down, say, Harry Potter. And I don't need all this. Author name, JK, and the rest is gone. Okay, let's try this out. All right. Okay, amazing. Okay, we can add more information, but for now, let's just leave it the way it is. Let's add some borrow info now and try to join it. Command C, Command V, get rid of this comma, that as well. Okay, so borrow ID 1, student ID, let's say 3, and Harry Potter, that's good enough. Book ID, let's say 1. And what do we have? Borrow date, say 29 June. And return date, let's put it as 29 August. It's a long time for a book. Okay. So that should be good. Book has no column called borrow ID. All right, I changed this as well. Borrow underscore info. Okay, should work now. There you go. Okay, now let's put these connections to test. Are you guys with me so far? Any confusions? Good so far. It's pretty easy, right? It's pretty self-explanatory. Even the language, it's very similar to our language. It's not really a programming language like that per se. Okay, so now say I want to see all the information of our students or the student who borrowed the book over here, which is Harry Potter. Let's just first see the student information. So for seeing queries, we always use select first. So select is what we use. So I'm gonna write down select, then a star sign. Star sign means everything inside the table. So when you use star and select together, it's just gonna display everything over there. So select star from, and in this case, borrow info. Borrow, okay, I wrote it wrong. Borrow info, and I'm gonna write down inner join customers, students actually in this case, my bad. So we are inner joining the students table. That's all small actually. STUDNBTS. Okay, what's up with my caps lock over here? Students. All right, inner join students on. Okay. Then borrow info dot customer ID or student ID. student ID is equal to, in this case, students dot, this would have caused an error, student ID. Okay, this should be good enough. We should be able to see something. There you go. So this essentially is showing everything related to the student as well. So we use the student ID over here, which was a primary key in the student table and a foreign key in the borrow table. We use that to join the two tables to see the information of the students as well as the borrow information, the book ID and whatnot. Does that make sense? Everyone? Let's try to do something over here. Let's try to, okay, no, that's not how it works. Command X, no, why is, this is so buggy. Anyways, let's try an inner join again, actually. Or, I'm just wondering if I can do it all together in one line. Yeah, we are essentially getting information from specific tables. So I will have to inner join again. Inner join. Just hope this lets me do it. So the other one was book. Can just copy this actually. Command V. Let me see the chat. It is using the primary key of one matching the foreign key of the other to connect both tables together. Yes, you are correct. Then okay. It's not borrow info anymore. It's okay, no, it is borrow info, but it's not student ID, it's book ID. Okay. And this over here changes to book. And this changes to book. All right. This should work, logically speaking. No such table as inner join. What do you mean? Oh, it's just not taking it like that. Understandable. Okay, so we might have to do it separately. Okay, this is getting annoying. Okay, finally it's gone. But at least we can see this one table over here. I think we are out of time as well. All right, so this is a very basic way of seeing the whole thing. In the next lecture, we're probably going to see a few more SQL queries as well. But for now, is everything clear for you guys? Do you guys understand the basic ones that we've used? So we've used drop to delete the table. We have used select to view the table. We used inner join to join the two tables based on the primary key and the foreign key. And we have used the create table to actually make the tables themselves. Any questions, anyone? See in the chat, what's just saying, I mean, does join going Yes, join will essentially join both the tables based on one common, what do you call it? Attribute. It's kind of like a Venn diagram, to be honest. Let me see if I can draw it. Yeah, it's kind of like a Venn diagram. It's like this. Okay, no, that's not a good Venn diagram. But yeah, it's kind of like this. So it's the two tables over here working. So this over here is the student. And this over here is, well, I believe, borrow info. And in the middle, we have our customer ID or student ID, actually, sorry. Student ID. Does that make sense? It's something similar to this. It's like a Venn diagram. So is it linking just the student ID? It's using the student ID to link the whole table. Yeah, it's using the student ID to create the link and displaying the whole table. So I mean, in order for them to join, they need a common ground, right? That's for anything. In order to join two things, you'll have to have a common ground for them to join on. So over here, it's student ID. Everything good so far? Understandable? Any questions from this lecture? If everyone could answer, that would be really appreciated.
Steve, you can just give them an example. You know, the output, you are only getting borrow ID 1, right? Because the borrow ID is coming from borrow info, and borrow info has just one element.
Yeah.
So if you can explain it by examples, because only one is matching with the customer. No, which is the student.
Oh,
Oh,
I think I understand what you're saying. So the thing is, you're not going to see the whole table. What you're seeing is only the ones that are kind of there or that are matching. So if I had more student IDs matching with borrow info, they would appear over here as well. So if there was a student ID 2 as well over here, student ID 2 would appear after this. It's not just one coming up. I can add more definitely. Let me just Command X. Let me insert into. Okay, insert into. Let me just copy this real quick. Oh no, that's gonna go off. Okay. So for borrow info, I'll just copy these, Command C, get rid of that, get rid of that, get rid of that as well, and that too. Okay, so that's done. In the next line, I will be writing insert into, and then I have values. And over here, the first one would be, say, my borrow ID is gonna be 2. Say student ID is gonna be 2 as well. Since book we only have 1, I'm just gonna write 1. And I'm gonna write in a borrow date of, say, 20 Jan. And return date of 20 Feb. Okay, need another over here. All right, that's good. So let me close
maybe
this off.
if you can change the student ID to 4. Do you have a force? Do you have the do you have four students or 3? Or change
We
it
have
to
3.
3. Just change it to 3 so that we can show that a 2 can match a 3, you know.
Oh, the student ID over here I'm showing in the output already before. That was already a 3. If you want, I can try 1 over here.
Yeah, one different, something different. Yeah.
Yeah, that works too. So, okay, let's put a 1. So let's do a run SQL. I think I'm missing something. Error near syntax. Okay, I think I made a mistake. It seems okay. Comma, comma, comma. That's good. Is everything okay over here? Oh, that's why. I did not write which table I am putting this in. Borrow info. Okay, now run. Successfully done. Okay, so now let me go back to my notes. Copy this and see. Get rid of this. Okay, so now it should show both. See? So now I'm seeing both the students with student ID 3 and student ID 1. So the last query, we were just adding another borrow or another transaction to our borrow info table. This is just to show you guys an example that it doesn't show one by one. It will actually show every single student ID that matches. In this case, 3 and 1, both of these match over here. So, I mean, both of these exist, so they will be joining. If they didn't exist in the student ID, likely it wouldn't join or show. Does that make sense? Everyone, does that make sense? Any questions? Novita, does that answer your question as well? All right, perfect. Yeah, I mean, that's about it for the very basics. There are a lot of queries, but you will be using these for the most parts. I mean, we'll see a few more in the next lecture, but for now, I would say this will be it. Is everything understandable? The basics of everything? We understand how to draw schematic diagrams. We understand how to go for basic SQL queries and how they change everything. We saw how to drop the tables. We saw how to insert. We saw how to show something, display something. We saw how to join something. Is everyone clear on every single part of these, or do you want me to repeat anything? Just let me know in the chat if you want me to repeat any part. All right, clear so far, amazing. Is that for everyone? All right, perfect. Okay, so if that's it, then I will stop sharing over here. And we can go on a 10-minute break. We will come back for our lab afterwards, all right? See you guys in 10 minutes.